In this video, we're going to be talking about hypothesis testing with one sample. We will be talking about null and alternative hypothesis statements, and we will be using Rguroo as our technology to assist us. So let's talk about hypothesis testing. So consider the following. If we had a car manufacturer who really wants to sell cars, they want their cars to look good. So they tell you any perks, any pluses for their car. So they come out and they tell everyone that this certain model of car that they make, it averages more than 38 miles per gallon on the highway. Everybody wants good gas mileage, right? So the question is, how do we know they're telling the truth? How can we verify what they say is true? Does the car really get more than 38 miles per gallon, this model of car? Or are they just saying that to get you to buy it, and it's actually not really true? So we can do something called a hypothesis test, where a claim, such as the one the manufacturer claimed about their car, where a claim is made, and we call that a hypothesis, and then we test it to see if it's true. And we test it by collecting evidence. The evidence is in the form of sample data. As we go through this process, you're going to see some similarities to confidence intervals. That's where we estimated a population mean or a population proportion, and we narrowed it down to a number within a certain range. And we use that to make some conclusions about the data. And hypothesis testing, a lot of times you will make the same exact conclusions that you would make with the confidence intervals, but it's just a different way of going about it. In hypothesis testing, it's very much like a criminal trial, and you're going to hear me talk about how different aspects of hypothesis testing is like a criminal trial throughout this video. And I do that because I think there definitely are similarities, and I think a lot of times people understand those basic parts of a criminal trial, especially if you've watched shows like Law and Order or movies where there was a court case, or, obviously you probably studied it in school as well, but you're most likely familiar with what goes on in a court trial. So when you do a hypothesis test, you start off by making two hypothesis statements, and these statements are contradictory to one another. And this is very similar to a criminal trial. In a criminal trial, you have a defendant who's been charged with a crime. And so right off the bat, you have two sides. You've got the lawyers for the prosecution, and you've got the lawyers for the defense. And the lawyers for the prosecution are going to come out and they're going to make their opening statements to the jury. And they're going to say, "We believe the defendant is guilty." And then the defense side will come up to the jury and they will make their opening statements, and they are going to say, "We believe that the defendant is not guilty." Well, it can't be both. Either the defendant is guilty or the defendant is not guilty of the crime. And those are two contradictory statements. And so that's what we're going to do with hypothesis testing. Right off the bat, we're going to come out with two statements. They're not the statements guilty or not guilty, but there are some similarities that we'll talk about when we get to those. Anyway, the basic thing that you need to remember, though, is the two statements will be contradictory. And then you're going to collect your sample data, which will be our evidence, and we are going to use that evidence to make a decision in favor of one of those two statements, such as what the jury does, because at the end of the trial, the jury says we find the defendant guilty or not guilty. So let's take a problem that hopefully you're familiar with if you viewed the videos for confidence intervals. This is a problem that we did in that video. So let's just review what it said. A machine that fills cereal boxes is supposed to put 20 ounces of cereal in each box. A simple random sample of 6 boxes is found to contain a sample mean of 20.25 ounces of cereal. It's known from past experience that fill weights are normally distributed with a standard deviation of 0.2 ounces. Construct a 92% confidence interval for the mean fill weights. And so you can see I have the answer that we found right here. There were 2 ways to do that. The first way is to use a formula, and we would use the formula that I call the Z interval formula. And we're using that because they gave us the population standard deviation, and that formula was X bar plus or minus Z alpha over 2 times sigma over square root n. And X bar would be your sample mean, which was your 20.25. Your Z alpha over 2 is your critical value. That's the number of standard deviations away from the mean that the boundaries of that 92% are. So it's the number of standard deviations. And so you would have used the Rguroo probability calculator. You would have clicked on continuous, and you would have figured out how far from the mean each of those boundaries would be. And I believe it's, just worked this one a little while ago, it's 1.751. And then you multiply that times sigma, which is your standard deviation, which would be 0.2, divided by the square root of 6. And you do this twice, once with a minus, once with a plus. And you can see here in Desmos, with a minus, you get 20.107. With a plus, you get 20.393. And that's what I have written right here. The other way to do it is with Rguroo, and you can go to Analytics tab, click on the Analysis drop down, Mean Inference, choose one population. Sample mean was 20.25. The population standard deviation was 0.2, and the sample size was 6. And the variable label, this was the mean cereal box weight. And then the confidence level was 0.92, and we chose Z statistic. And then you view, and you can see right here 20.107 and 20.393 when you round, and that's the exact same thing that we got before. So that was just quick review there. Okay, so let's talk about what that really showed. So up here, there was a claim made. This is a claim that's on the cereal box. The cereal box claims that it should have 20 ounces in the box. And so that's what the machine is supposed to fill the cereal boxes to, is 20 ounces. So what we want to know is, can we conclude that the average weight, the mean weight of the cereal is more than 20 ounces? Is it less than 20 ounces? Is it equal to 20 ounces? So what we can look at here is this entire thing, it's greater than 20. The whole thing is greater than 20. And again, this is an estimation of what the true mean fill weight is. So we're estimating that the true mean fill weight is anywhere between 20.107 and 20.393. So that entire range where the true mean, we believe it really is, that whole thing is greater than 20. So that means we can conclude that the average weight is more than 20 with 92% confidence. Again, because the entire interval is above 20. And so, we made some conclusions about the population there. We concluded that it's overfilling, the machine is overfilling the boxes based off of this confidence interval. Now, if our answer had been 19.88 to 20.56 and the true mean had fell between those two numbers, we wouldn't have been able to make the same conclusion about the machine overfilling, because 20 is included. 20 is within the 19.88 and the 20.56. So we can't conclude that the average weight is more or less than 20 ounces because 20 would be included. So we wouldn't say that the average weight equals 20 ounces. And for that, I want you to think about this. We never say that we find the defendant innocent. Have you ever noticed that? We only say we find the defendant guilty or not guilty. We never say we find the defendant innocent. So we can never say that we find that something is equal to an exact number. We can only really conclude an inequality. We can either conclude that it's less than, we can conclude that it's greater than, or we can conclude that it is not equal to. Or we don't have enough evidence to prove one of those three statements: less than, greater than, or not equal to. We would never say that we've proven that something equals an exact number. So the only thing we can say again is if we can't prove that it's less than, greater than, or not equal to, we just say we don't have enough evidence to show that it's greater than, less than, or not equal to. If we did a hypothesis test with this example instead, we'd find the same conclusion. It's just a different way to go about it, but they usually do draw the same exact conclusions. So there are quite a few types of hypothesis tests that we will be doing in this class. There's one where you test a claim about a population mean and the population standard deviation is given. These will start sounding very similar to the confidence intervals that we found in the past. So if you recall, there was a confidence interval we found when we were estimating the mean and they gave us the population standard deviation. And then there's a hypothesis test where you test a claim about a population mean, but you don't know the population standard deviation. Instead, you know the sample standard deviation. And then there's a test when you test a claim about a population proportion. So you'll definitely see some similarities to the confidence intervals that we did in the previous chapter. Moving on, there are tests that test claims about two populations. So we test about the difference between two population means and the difference between two population proportions. And there's a couple other tests that we're going to do as well. There's a total of 7 types of hypothesis tests that we're going to be learning in this class. So you will have a chance to work all of them. In chapter 9, we're going to focus on these 3 right there. Testing a claim about the mean when you know the population standard deviation, testing a claim about the mean when you don't know the population standard deviation, but you might know the sample standard deviation, and testing a claim about a proportion. So in general, a hypothesis test tests a claim about a population parameter, and it's always based on a sample. So in every one of these problems, we're taking a sample, and we're using that sample data to make conclusions about the entire population. All right, so let's talk about those hypothesis statements. So this is like the opening statements in a trial. The lawyers, right? They come up to the jury and they make their opening statements. And we call those opening statements for a hypothesis test the null hypothesis and the alternate hypothesis. Now, I think it's spelled that way. So the null hypothesis statement is the statement for the defense. And the alternate hypothesis statement is the statement for the prosecution. right? At least that's the way I look at it. And we use special notations for each one. So for the null hypothesis statement, you're going to use this notation. It looks like H0 or HO, but it's actually H with a subscript 0 to the right of it. And for some reason, I couldn't get the font to do the subscript on this particular slide. So let's talk about the null hypothesis statement, HO. This is the statement that we assume is true unless we can prove otherwise. So think of it this way. Think innocent until proven guilty. That's what we're supposed to assume, although I don't think that happens so much anymore. I think people come in with some opinions, at least when we're watching it on TV. Hopefully the juries that they choose actually come in with an open mind and give the person a fair trial. But technically, they're supposed to be innocent until proven guilty. So we're going to assume that our null hypothesis statement is true unless we prove otherwise. So assuming it's true is like saying that it's innocent. Saying that it's false is like saying that it's guilty of the crime. So innocent until proven guilty is null. And then this, I think, is on another slide, but I want to put it here just in case it's not. The null statement is always an equality statement, meaning it either contains the equals symbol or it's a sentence that implies the equal symbol. Now, the alternate statement, again, that is a statement similar to what the prosecution would state. Now, the prosecution says that the defendant has committed a crime. So what they're saying is that the null statement is not true, and they offer an alternative to the null statement because they believe that the null statement is not true. And so they are going to say that it's not equal, it's an inequality instead. It's either less than, greater than, or not equal to. So the notation, again, it doesn't look like subscripts, but it should look like this. So you can have H with a subscript 1 or H with a subscript A. I usually write H1 myself, but you can write HA. You see it written both ways. So this is completely your preference. So you can write the alternate statement as H1 or HA, and this is always an inequality statement. So think less than, greater than, or this new symbol that you may have not used before, not equal to. Now, at the end of a trial, what happens? The jury deliberates the evidence, and then they come back and they either say guilty or they say not guilty. Now, the equivalent to that, the equivalent of guilty is saying that we reject the null. So if you recall, the null is what we're assuming is true until we prove otherwise. And so we're saying that that first statement is truth. So if we find the defendant guilty, we're really saying it's not true. So if it's not true, we're rejecting that statement. We're rejecting it because we're saying it's false. So if you reject the null, again, what you assumed was true at the beginning of the hypothesis test, if you reject it, you're assuming that it's now, you've proven it that it's now false. Again, same thing as saying it's guilty. Now, if you fail to reject the null, That doesn't mean that the null is true. It just means you don't have enough evidence to prove the alternative. So again, that kind of goes with we don't ever say we find the defendant innocent. We either say guilty or not guilty. So if we fail to reject the null, that means we don't have enough evidence to say that the null is not true. That's what that means. So then, this is important. We never say that we accept the null. Again, that goes back to we don't say we find the defendant innocent. We never say that. So we never say we accept the null, because accepting the null would be saying we find that the null is true. And again, you can't say that. You can either say we find the null false, we reject the null, or we don't have enough evidence to reject the null, meaning we fail to reject the null. So one of those two, we never can say that we accept the null. So important things to keep in mind as we move forward. Now, the null and the alternate statements, for these beginning tests, actually most of them, you're going to use mathematical symbolic statements. So let's start with the null. So again, I told you guys that the null hypothesis is always an equality statement. So check this out. There's always an equal sign. Now, you don't write two null statements. You only write one. But for the beginning, we're going to start by figuring out what kind of hypothesis test are you doing. Are you testing a mean, or are you testing a proportion? If you're testing a mean, then your null statement should start off with mu. If you're testing a proportion, it should start off with p. And so you'll make a statement about what you're assuming is true. So think about the cereal box problem. For that one, we were testing a mean, or we're doing a confidence interval for a mean. But if we were going to do a hypothesis test, we start with the mean, and the assumption is that the mean weight of the cereal is equal to 20, because that's what the box says. And that's all you would write for the null statement. That's your opening statement right there. Now, if we were testing a proportion, you would do use a capital P equals to some number. Okay, so when I have parameter written here, this is the number that we think that the mean or the proportion is equal to. In this case, 20. And then we have to make the alternate statement. And so you have basically three choices. You can either do less than, greater than, or not equal to. Again, because it is not an equality statement. It's actually an inequality statement. And the number that you use in the alternate hypothesis will be the same number you use in the null hypothesis. So because we used 20, we compared the mean to 20. You're going to be comparing the mean to 20 in the alternate hypothesis as well. Now, we believe, based on the evidence, that the mean is not 20. We believed that the mean was actually greater than 20. Because the sample mean was 20.25, which is definitely greater than 20. So in that case, I would use the greater than symbol. But notice the numbers on the right-hand side of each of these statements should be the same. They should match up. Now, you use less than if you think it's less, greater than if you think it's greater. And if you just think that it's different and there's no, excuse me, no specification on how it's different, whether it's less than or greater than, you use a not equal to sign. And if you're testing a proportion, again, you use p's instead of mu's. All right, so let's write a couple of these. It says, last year, the mean amount spent by customers at a restaurant was $35. A restaurant owner believes that the mean may be higher this year. Write a null and alternate hypothesis statements. So somewhere in here, there's a claim. The claim often comes across as a belief, such as in this case, the restaurant owner believes that the mean may be higher this year, or someone thinks something is different in some way. They actually use the word claim, but somewhere in there there'll be something that usually contradicts what a mean or a proportion was. So we're going to start by writing our null and our alternate statements. So I'm going to start by writing H0 and H1. And we're testing a mean. So I'm going to start off by writing the mu symbol so I don't forget. And also I remember that the null is always equals. Always, always, always. So what do we assume that it equals? So again, let's read it. It says last year the mean amount spent by customers is 35. A restaurant owner believes that the mean may be higher this year. So we're going to go with the assumption that it equals 35 because that's what it was last year. And again, we assume it's true until we prove otherwise. And then the alternate statement will be something that contradicts it. The owner believes that the mean may be higher. So for higher, guess what? We would use the greater than symbol. And again, the numbers have to match. These two numbers, these two symbols have to be the same. The only thing different is the mathematical operation in between the two. So, well, actually not operation, but symbol. So either equals or some sort of inequality sign. So HO would be the equal sign, the null, and the alternate H1 would be the inequality symbol. All right, let's look at another one. In a recent year, the mean weight of newborn boys in a certain country was 6.6 pounds. A doctor wants to know whether the mean weight of newborn girls differs. So the doctor wants to know whether it differs. There's your claim right there. But no matter what the claim is, we start off with what we are assuming is true until we prove otherwise. So again, we're testing a mean. Equal sign goes up here. And what we assume is true, we assume that it's 6.6 until we prove otherwise. And what are we trying to prove? The doctor wants to know if it's different for girls. So different would be the not equal to symbol, like that. Alright, so why don't you pause the video and you guys try this one, and then unpause the video and come back and we'll go over the answer. Okay, so hopefully you had time to work this. Example 4, gas mileage. A certain model of car can be ordered with either a large or small engine. The mean number of miles per gallon for cars with small engines is 20.5. An automotive engineer thinks the mean for cars with a larger engine will be less than this. So writing our statements, we're doing a mean again. The null is always equals. We're assuming that it's equal to 25.5 until we prove otherwise. And what does the automotive engineer want to see? If it's less than that for larger engines. So we would use the less than sign. Alright. Alright, a pollster thinks that less than 30% of registered voters, I'm sorry, let me read it again. A pollster thinks that less than 30% of registered voters in the county voted. So, null, alternate. We are not testing a mean here. They're talking about percentages. We're testing a proportion. So we're going to use a P. Remember, the null is always equal. We're assuming that it's equal to 30%. This is actually the way you probably should go ahead and write it in decimal form, only because when you put this into Rguroo, it needs to go in decimal format. And then the alternate statement is he believes that it's less than 30. So the way I would write it is probably this way, in decimal form. All right. Pause the video and try this one. All right, we want to test whether the mean GPA for American college students differs from 2.0. So we're testing a mean, and the null is always equals, so always write that. And we want to know if it differs from 2.0. So again, the numbers have to match up. So we're assuming that it's equal to 2.0 until we prove otherwise. All right, placement tests. In an issue of U.S. News and World Report, an article on school standards stated that about half of all students in France, Germany, and Israel take advanced placement exams in a third pass. The same article stated that 6.6% of the U.S. students take advantage of placement tests and 4.4% pass. Test if the percentage of U.S. students who take advanced placement tests differs from 6.6%. So we're talking about percentage. That's just another form for a proportion. So we're going to use P. And always remember the null is equals. So we're testing if the percentage of U.S. students who take advanced exams differs. So differs from 6.6%. So again, use the same number there. I would actually write it this way instead. P equals 0.066. And H1 I would write as P is not equal to 0.066. Okay, so moving on, we have something called type 1 and type 2 errors. So since H0, the null, and H1, the alternate statement, are contradictory, only one of them can be true. So if the null is true, then that means our conclusion should be that we fail to reject it because we believe it's true, right? Or because it is true. So we're going to we're going to fail to reject it. And if the null really is true, we have made the right decision. If the null is false, we should reject it instead. And if we do that, then we've done the right thing because it's false, so you should reject it. But on the other hand, we can make mistakes. We can make the wrong decision. So if the null is actually true and we reject it, then we've made a mistake, and that mistake is called a type 1 error. So you only make a type 1 error. You make a type 1 error if the null is true and you reject it. So if you reject the null and it was a mistake, that's important, then that's called a type 1 error. If you fail to reject the null and that was a mistake, because the null is actually false, then that's called a type 2 error. Because if the null is false, you should reject it. But if you fail to reject it instead, making a mistake, that's called a type 2 error. So type 1 errors happen if you reject the null and it was the wrong decision. And type 2 errors happen if you fail to reject the null and it was a mistake, so you made the wrong decision because the null was really false, so you should have rejected it instead. So again, type 1 errors happen when you mistakenly reject the null, and type 2 errors happen when you mistakenly fail to reject the null. So let's look at some analogies. We've got the medical test analogy. So if the null is you don't have a disease, and I'm going to write the alternate statement here. If the null is you don't have the disease, the contradictory statement would be that you do have the disease, right? So a type 1 error is when you mistakenly, let me rewrite that. You mistakenly reject the null. So what you're saying is you're saying you rejected that. And if you reject that, then that means you think you have the disease. But again, it's an error. So that's really not true. You really don't have the disease. So in that case, that would be a false positive. Right? All right. So check out a type 2 error. Rewrite that. Type 2 error is when you fail to reject the null. If you fail to reject the null, you can't prove H1. So we can't, if you fail to reject the null, you don't cross the null off. That means you have to cross H1 off. So if you fail to reject the null, then that means you believe you don't have the disease. But because you made an error in your decision, you really do. Which is the worst scenario, I think. So obviously you're sick and you need to get treated, but you don't realize you have the disease, even though you really do, based off of that. So again, type 2 errors only happen if you, type 2 happens if you fail to reject the null and that was a mistake. And type 1 happens if you mistakenly reject the null. So let me add this here in the notes. This is type 2 is when you mistakenly fail to reject the null. Alright, so let's go over to the trial analogy. HO is that you're innocent, which means that H1 would be you are not innocent. So type 1 error. I find it helpful to do this. Type 1 is when you reject the null. So we mistakenly reject the null. And in that case, we support H1 that you're not innocent. So this is where we say the defendant is guilty when they aren't, which is bad, right? You don't want an innocent person to go to jail. So a type 2 error, let me rewrite this. Is when you fail to reject the null, but you really shouldn't. So if you fail to reject the null, then you're not saying the null is true, but most likely the null is true. So basically, in that case, you mistakenly fail to reject the null. And if you fail to reject the null, you don't have enough evidence to conclude H1. So you don't have enough evidence to say that the person is guilty. So instead you say they're innocent. And so in that case, they're guilty, but you said they weren't, which means they get the get out of jail free card because they were not found guilty. We failed to reject the null. All right. So a type 1 error means incorrectly rejecting the null, and a type 2 means incorrectly failing to reject the null. All right, so let's look at some scenarios, some real world scenarios, and we're going to put the type 1, type 2 error spin on it. Suppose Frank tests his rock climbing equipment, and the HO is that the equipment is safe. All right, so I find for these, it's helpful to try to write it out. So I start off by writing the two statements. The null is that the equipment is safe, and the alternate is that the equipment is unsafe. All right, so type 1 error means you incorrectly reject the null. So this is what we're doing. We're rejecting the null. And if we reject the null, that means we have enough evidence to conclude the other statement. We're saying that this is what we're saying. We're saying that the equipment is unsafe, but it really is safe. That's what a type 1 error would mean. All right, rewriting this again, I'm just going to say HO is safe, and then H1 is unsafe, just to save time. So if we do a type 2 error, that's when we incorrectly fail to reject the null. So if we fail to reject the null, that means we don't have enough evidence for the alternate statement, and most likely we're saying that the null is true. Now, we can't say that in our conclusion, but that's kind of the assumption that you make. So what this would mean here is we say it's safe, but in truth, it isn't. And that is worst case scenario, because it's rock climbing equipment. I'm assuming for mountains and that kind of thing, so those go pretty high. And so in the type 2 error scenario, we're saying the equipment's safe, but it really isn't. And so that could be bad. All right, so why don't you pause the video and do example 2. A victim of a car accident is brought to the emergency room, and HO is that she's alive when she comes in. And see if you can figure out what a type 1 and type 2 error each of those would imply. Okay, hopefully pause the video and work that. I'm going to write the null and the alternate statement. So the null is that she's alive, which means the alternate is that she is not alive. So let me write this again. I find it helps to have it written out so I can cross off things. All right, type 1 error. So type 1 error is when we incorrectly reject the null. So what we're saying is that. So in this case, we say she is not alive, but she really is alive. That's what a type 1 error would be here. And then for type 2, this is, I'm going to rewrite this part here, sorry, bear with me. HO is alive, H1 not alive. Okay, so a type 2 error happens when you fail to reject the null. So if we fail to reject the null, we don't have enough evidence to conclude that. So most likely we're saying that she's alive. So this is where we say she is alive. But that was a mistake because she really is not alive. So I think, both are pretty bad. Second one is, I would say, is worse. All right, so let's talk about the 3 types of tests that we're going to be doing in this section. We have a z-test. This is when you test a claim about a population mean and you know the population standard deviation. Then there is there's a t-test. That's also when you test a claim about the population mean, but this time the population standard deviation is not known. However, the sample standard deviation is either known or you can find it. And then both of these are mean inferences. This one here we call a 1-prop z-test, because that's what it's called in the previous calculator that I used to use for the class. But it's a proportion inference. And you use this when you're testing a claim about a proportion. So those are the 3 that we're going to be working on. Okay, so once the data is collected and the 2 statements are made, we run a test. If we're doing a trial, the trial goes on, and once all the evidence is presented, the jury goes back and they deliberate and they draw a conclusion. So when we make a conclusion here, it's based off of how likely the evidence is to be true. How likely is it to occur? So check out this example. Didi and Ali are at a birthday party of a very wealthy friend, and they hurry to be the first in line to grab a prize from a tall basket that they can't see inside. So it's one of those things where you reach in and you pull something out, think probability. So there are 200 plastic bubbles in the basket, and they have been told that there is only one $100 bill. So Dee Dee is the first person in line, and she reaches into the basket and she pulls out a bubble, and her bubble contains the $100 bill. How likely was that to happen, right? So if you think about it, the probability that she's going to pull out the prize bubble with $100. They said there's 200 plastic bubbles, but only one contains that. So it's 1 out of 200. So 1 out of 200 is 0.005. That's a very low probability. That probability is very unlikely to happen. If you'll remember, we consider, up to this point anyway, we've considered anything less than 5% to be unusual. So 5% is 0.05. This is definitely less than 0.05. This is 0.005. So it's very unlikely that this would happen. And because this is a rare event, they begin to doubt that the information they were given at the beginning of this game was actually true. So, because it's so unlikely to happen that the person would pull out this bubble and win on the very first try. So, because it's so unlikely, in reality, they would weigh this against the probability that the person who told them that they had lied about how many prize eggs were actually in the basket or prize bubbles. And if they trusted the person they wouldn't doubt their word because they had assumed that the probability of the person lying was even lower than 0.005. So that's kind of how you make the decision. You collect the evidence, and what we actually do is we take a sample, and then you calculate that sample statistic, so the sample mean or the sample proportion, depending on what it is that we're testing, which type of parameter. So you take the sample, and you are going to get, so let's take like the cereal box example. Took the sample mean, we got 20.25. Now that is greater than 20, which is what the cereal boxes said it was supposed to have. It's greater than 20. So here's the question. If we took a sample of 6 boxes, how likely is it that you would get a weight such as 20.25 if the true cereal weight was actually 20? So if your assumption at the beginning, in this case the null statement, if that's actually true, if the mean weight was really 20, how feasible is it that you would get, if you took a sample of 6 boxes, that you would get a sample mean of 20.25? I mean, it's bigger, and it's understandable that sometimes your sample mean will be a little bit higher than the population mean, and sometimes it'll be a little bit lower. But, how extremely high can we get? Is 20.25, is that extremely higher than the 20? Is it something that is very unlikely to occur? And if that's the case, then we start to doubt whether that assumption that the cereal box weight really is 20, whether that is actually true. And so we use that to help us make our decision. So let's talk about some assumptions. We make the assumption about the null, that the null may or may not be true, but we make that assumption at the beginning. We assume it's true until we prove otherwise. So if the sample that we get, the sample statistic, the sample mean or the sample proportion, is reasonable result based on the assumption we made, we don't reject the null hypothesis. We fail to reject it. That means that the sample mean or the sample proportion, the probability of getting that is bigger than what we consider to be an unlikely probability, an unlikely event. So usually 0.05, but we can switch that up. And if the sample we got is really unlikely, so the probability of it occurring is less than, well, again, normally we say 0.05, but again, we will start changing that a little bit. If it's less than what we consider statistically significant, then we reject the null hypothesis. And what that means is basically we're saying this is so unlikely to happen because the probability is so small if the null were actually true, which means the null probably isn't true, because this is really unlikely to happen. And if the null is not true, then we can conclude that the alternate is true instead. And that's kind of how that works. Now, when we are trying to figure out whether it's likely or not, we actually calculate a probability. So the way we measure a rare event is with what is called a p-value. And so a p-value is the probability that if, I'm going to use a different color here, if the null hypothesis were true, that we would get a sample as extreme as we did. So assuming the null is true, if the null is true, what's the probability that you would get your sample mean or your sample proportion? And if that probability is low, then that must mean that our assumption is false, so we reject the null. And if the p is not low, then it's likely to happen, so we can't reject the null. We can't assume that it's false. So what do we consider low? In the past, we have considered anything less than 5% to be low, but we're going to introduce this notation here, which we actually have seen this notation with critical value, but this is alpha if you will recall, and it is the significance level. And it's what we consider the cutoff for being a low probability. So in the past, we've used 0.05 as what we consider the cutoff. Anything less than that, we would consider consider a low probability, unusual, if you will. But we can redefine our significance level. We can redefine it as 10%, 0.10 instead. And we can say anything less than 0.10 we consider to be unusual. We could say it's 0.01. Anything less than 0.01 we consider unusual. So we define that when we're doing the hypothesis test, and it's what we consider to be unusual. Now, that's normally given in a hypothesis test question, but if it's not given, we assume the significance level is 0.05. And if you want to get technical, alpha is the probability of making a type 1 error. All right, so finding the p-value, there are different ways to do it, but the quick way that we're going to use is with Rguroo. The steps you're going to find is very similar to when we did the confidence intervals. All right, so you're going to go to the Analytics tab. You're going to choose Mean Inference or Proportion Inference, depending on what you're testing. And you're going to choose one population. So, Analytics tab, Analysis drop-down, choose Mean Inference, choose one population. That's what we do at the beginning. Now, excuse me, only one of these boxes will come up. Well, actually, the first two boxes, these are the same. But I want to show you kind of how they're, you would enter numbers in different places depending on what the hypothesis test you're doing, what type of data we have. So if you're testing a mean, and the population standard deviation is given, it's known, then you are obviously going to choose the mean inference in one population. And then if you're given a data set, if you're testing a data set that you already have, you can choose your data set and your variable. But if not, you're just going to come in here and you're going to fill in your sample mean. You're going to fill in your population standard deviation, and you're going to fill in your sample size. And then just like for confidence intervals, you're going to fill in your variable label. Now, here's the difference. You are going to choose the Test of Hypothesis tab. Before, we kept it on the confidence interval tab. Now we're going to do the Test of Hypothesis tab. And actually, you can toggle back and forth, and you can do both of them at once. You can find a confidence interval and test your hypothesis at the same time. So then once you fill those pieces in, you are going to fill in your significance level. And then you are going to fill in your alternate statement. So your alternate statement is either that it's less than, greater than, or not equal to. So that'll be a drop down. You choose the correct one, and then you enter your value here from your alternate statement. This is your H1. And then if they have given you, again, the population standard deviation, you're going to choose the statistic, and then you're going to choose preview. And when you do that, you're going to see what the p-value is. And then you're going to use that to make your decision. If you're testing a mean and they give you the sample standard deviation, or they give you at least the raw data so you could find the sample standard deviation, you are going to still choose mean inference, and you're going to choose one population. This time you're going to fill in your sample mean, your sample standard deviation, and your sample size. You're going to fill in those three, as well as your variable label. significance level, and then your alternate statement. This is still H1. But this time you're choosing T statistic. The difference between the first one and the second one is what type of standard deviation did they give you, sample or population? All right. Last, excuse me, if you are testing a proportion, then you're going to choose a proportion inference instead of a mean inference, one population. And you need to fill in the sample size and then label the units. You need to fill in the number of successes and label the units. And then you need to fill in the alternate hypothesis statement. And then you need to check large sample Z. Oh, and then you also don't forget the significance level is here on the right. So the significance level is right here. You want to fill that in. And then for any, excuse me, I'm trying to sneeze. Or I thought I was going to, but I stopped. For any of these, once you fill everything out, you're going to hit the preview button, and that's going to give you your p-value once you do that. All right. So again, going back up here, what do we do with the p-value? If the p-value is low, we reject the nulls. If the p-value is less than or equal to the significance level, you are going to reject the null. And if the p-value is greater than the significance level, you're going to fail to reject the null. And then from there you make your conclusion. So you make your decision to reject or fail to reject based off of the p-value. You compare the p-value again to the significance level, and if it's less, reject the null. If it's greater, fail to reject the null. So let's go back down here, and I have two examples that we're going to work through really quick. And, well, maybe not really quick, but we're going to work through two examples, and then that'll be it for this section. So, a social scientist suspects that the mean number of years of education for adults in a certain large city is greater than 12 years. She surveys 100 adults and finds that the sample mean number of years is 12.98. Assume the population standard deviation is 3 years. Test the claim. So let's find the claim. I like to highlight it if possible. A social scientist suspects that the mean number of years of education for adults in a certain large city is greater than 12. So I'm going to start by writing the null and the alternate statement. That's always where you start after you identify the claim. So we're testing a mean. So I'm going to start by writing mu, and recall the null is always equals. So the social scientist suspects that the mean number of years of education for adults in a certain large city is greater than 12. So I went ahead and filled in the alternate statement based off of the claim, and then remember the two numbers have to match. All right, so now that I've written that, I need to decide which type of test am I going to run. Am I testing a mean or am I testing a proportion? We're testing a mean. So I'm going to do a mean inference. And this is one population. That's what I'm going to do. And then the big thing once I get here is deciding whether or not I'm using the Z or T. And that depends on the type of standard deviation they give you. So let's look at this. She surveys 100 adults and finds that the sample mean is 12.98. And we assume that the population standard deviation is 3. So they gave us a population standard deviation that means we're using a Z. That's what that means. All right. So I like to just go through here and fill in some things that we know. We know the sample size is 100. We know the sample mean is 12.98. The population standard deviation is 3. And we also need a significance level. They don't give us one. So if they don't give us one, assume it's 0.05. Okay. So there we have it. That's all the info that we need. Oh, also real quick, they might ask you which type of tail you would need for this test. So if it's greater than, that is a right-tailed test. And when we do this in Rguroo, it will do an illustration of a curve with some shading, and you will see that this will be right-tailed. But let me just show you for H1, if it is less than, we're going to say it's right-tailed. If it's greater than, we're going to say that it is left-tailed. And if it's not equal to, we're going to say that it is two-tailed. All right, so just keep those in mind as we're going through. All right, back to the question here. We're doing a one population mean inference, and we're doing a Z because we know the population standard deviation. So let's go over here to Rguroo. We're going to click on the Analytics tab, choose Analysis. We're testing a mean, so choose Mean Inference. Proportion inference is above it, so Mean Inference, one population. A box will pop up. We know the sample mean is 12.98, and we know the population standard deviation is 3, and we know the sample size is 100. All right, and then we're going to label the variable name, and the variable we're looking at the mean number of years of education for adults in a certain large city. All right, and then confidence interval is right here. I'm going to click over to test hypothesis. Significance level, the default is 0.05, so if they don't give one, leave that. If they do, you can change it accordingly. This needs to match up with my alternate statement. My alternate statement is that it is greater than 12. And I just noticed something. I will actually tell you what I noticed in just a moment. So hopefully you continue watching the video so that you don't miss a mistake that I made. You may already be aware of the mistake on the previous screen. Okay, so going back to this, and then I'll explain what you need to change up in your notes. You are going to click Z statistic. Again, Z statistics gets clicked if you know the population standard deviation, and T statistics gets clicked if you know the sample standard deviation instead. And then we'll hit preview. All right, so a lot of stuff is going on here. We've got a variable, sample size, mean, population standard deviation. Then you have a second thing here with a sample mean, standard error, observes Z-stat. This here, in Newton, this one right here, in Newton, it's going to ask you for what is called a test statistic. And I'll kind of explain what that is in a moment. But if they ask for test statistic, that's where you get it from. And then it has a critical value, and then it has your p-value. So here's the p-value right here, and the p-value is 0.0005. Okay, so I'm going to write that down. So you guys write that down. P-value is 0.0005. All right, now this is what I want to show you. All right. So you've got two graphs at the bottom here, and they're kind of showing the same thing, but they're highlighting something different in both. So if you had the observed data, the sample mean we found was 12.98, and it falls right here where this little triangle is. And so the probability that it would occur, the shading would happen right here, but it's so far up here, it's so hard to see. Anyway, what is shaded is 0.00054411. So basically up here is the probability that we would get a sample mean of 12.98 when the true mean is really 12. All right, which is a low probability. Over here is if we took all of the data and we converted everything to a z-score, then this 12.98 would be converted to a z-score of 3.2667, which is here. And again, it would have the same probability of occurring. So that's what those mean. Now, the shading you notice is on the right side. So this is where that right-tailed comes in. Okay. So now I'm going to go back to the slide, and I'm going to finish this one out, and then I'm going to show you my mistake where I wrote a mistake in the notes, and we're going to fix it. Okay, so your p-value, you're going to compare that to your significance level, which is 0.05. 0.0005 is less than the significance level of 0.05. And if it's less, that means it's unusual, unlikely. Right? So what is unlikely? It's unlikely that if the true mean really were 12, that if you took a sample of 100 adults, that you would get a sample mean that is 12.98. That's 0.98 bigger than the true mean. That's if it were equal to 12. So what we're saying here is this is very unlikely to happen, to get a sample stat that much higher than the true mean if the true mean is really 12. So most likely 12 is not the real mean. That's most likely the case. So our decision here is that we're going to reject the null. We are rejecting it. And if we reject the null, then we have enough evidence to conclude the alternate statement. So we're actually going to write a conclusion statement. And think about how we wrote the interpretation sentences for confidence intervals. I gave you a little template, so I'm going to kind of give you a little template here. All right, so you're going to say that either there is or is not. So that's what would go here. Is or is not. And let me leave a little space there. Is not. All right. So you're going to fill that in there. There is or there is not enough evidence. The evidence is the data. To conclude that, and then you're going to basically you're going to put in H1 in context. So H1 said that the mean is greater than 12, but you got to put this in context. So you would say H1 is that the mean years of education is greater than 12, and I ran out of space there. So I'm not finished because I never did fill in this top here. So again, if we're rejecting the null, we're saying that most likely it's not 12, it's not 12, then most likely it's greater than 12. So that means there is enough evidence. So when you reject the null, there's enough evidence to conclude H1, and when you fail to reject the null, there's not enough evidence to conclude H1. All right, so what did I mess up here? So I told you down here that greater than is right-tailed, but look what I wrote up here. I wrote it the reverse. So let's fix that. It actually goes the direction that the sign is pointing. So we would say less than points left, so it's left-tailed, and greater than points right, so it is right-tailed. All right, so let's do one more. Test scores. A pre-test and post-test test were given to workshop attendees. The pre-test score average was 24. And the researchers want to know whether the post-test score is significantly different from the pre-test score. They sampled 50 tests and found that the sample mean was 24.8. Assume the population standard deviation is 1.2. Use a significance level of 0.01. So where is this claim? Researchers want to know whether the post-test score is significantly different than the pre-test score. So we're going to use that to write our null and our alternate statement. We're doing a mean again. Again, the null is always equals. We're assuming that the post-test and the pre-test are equal. The pre-test score was 24, so we're assuming they're both equal to 24. The alternate statement is the researcher wants to know whether the post-test is different. So they're not specifying less than or greater than. So in this case, we use not equal to. Same number, 24. Now, we're testing a mean. So it's a mean inference. So a mean inference. And it's a one population. And we know population standard deviation. And so we're going to use a z. It's going to be a z interval. Also, because this is not equal to, we're going to say this is two-tailed if asked. All right, so let's fill in some things we're going to need to put in. We need to know the sample mean, and the sample mean is 24.8. The population standard deviation is 1.2, and the sample size is 50, and the significance level they defined as 0.01. Okay, so we're going to go to our Rguroo, and we're going to go to Analytics, choose Analysis, Mean Inference, one population. The sample mean was 24.8. The population standard deviation is 1.2. Sample size is 50. Don't forget to label your variable. So this is, we're testing whether the post-test scores are higher than the pre-test scores. So we're trying to test the mean of the post-test scores. All right, and we're going to test our hypothesis. So click Test Hypothesis. Significance level, we're going to change to 0.01, and we want to know if it is not equal to different. So not equal to is this one here, 24. And we're going to choose Z statistic again and preview it. And it looks like the p-value is 2.0. oops, 2.4247 e negative 6. Okay, so looking at that, we need to convert this to scientific note. This is in scientific notation. We need to convert it to regular notation, regular decimal notation. So we're going to move the decimal 1, 2, 3, 4, 5, 6. So you actually kind of add 5 zeros in front. So we've got 0.0000024, and that is definitely less than 0.01. So if it's less, remember that you reject the null. And that is our decision. And because we reject the null, we can conclude H1. So we would say we have, or we would say there, this is conclusion, by the way, there is or is not, we would say there is enough evidence to conclude that H1, and H1 in context is that the mean post-test score differs from 24, or differs from the pre-test score, which is 24. And that's our conclusion. I did want to show you something really quick. I just want to go back real quick into this. Go back to basics and click on the confidence interval tab. And we did 0.01. Let's do 0.99 and choose Z statistic. If I click preview, not only do I have my hypothesis test here, below it, I now have the confidence interval, and you can see that the confidence interval, we are 99% confident. The true post-test score is between 24.36 and 25.24, right? So I just wrote that down on my slide there at the bottom. This is the 99% confidence interval. And so what I want to tell you is, did the two of these agree? Does this conclusion agree with this? Well, this suggests that the mean is greater than 24 because the entire confidence level is greater than 24, and greater is different than 24. Right? And that is what we concluded. So these two, they agree. Right? They agree. All right. So that is all for this section. We are going to do more confidence intervals and more hypothesis testing. We're going to do more examples in the next section, in the next presentation. So no worries. Definitely more examples. This presentation, I really just wanted to kind of show you the basics and the concept of hypothesis testing, and then we, maybe do a couple of examples, and then we're going to really dig into it in the next section. All right, have a good one. If you have questions, let me know.